Yeah, they're coming in.
Thank you, sir.
Give it another 45 seconds. Okay, I think let's get started while we wait for people to come back into the room with full capacity. This is a session on Mori bands, and we are very pleased to have Jeanie Lau to start off. Please.
All right. Okay, thank you. Right, thanks, Gmail, of course, and Xiao, Pengcheng, Ming, and friends for organizing this fantastic conference. Not only for this great talks and discussion, but also arranging for the great weather and the great food. So I'm also, of course, happy just with any skills to travel to meet new and old friends. Okay, so today I'm going to tell you about our work on the helical edge state and supercurrent in topological van der Waals materials. I know, well, Gmail said this session on Mori materials, I'm actually only going to have 2 slides on the Mori, but we'll see. Okay, so this is kind of a brief outline of the talk. I'm going to tell you about 3 projects that's going on in my group. First is this transport data on business iodide transistors. Second talk is on helical edge states and field layer graphene. And third one, this is only going to be 2 slides about our work in this superconductivity in twisted bilayer graphene, which of course has a flat band, and we think we've seen the evidence that's enabled by quantum geometry. Okay, so first let me tell you about the first work on business iodide. And this work is a truly team effort. So it's, the transport studies is led by my student Yulu Liu. And this is our team, the DMREF team. So the crystals are made by Bing Lu's group, and the theoretical calculations by Fan Zhang. And of course, Ming and Bob did the fantastic RPERS measurements. Okay, so I think Fan and Ming have already given great introduction and great talks on business iodide. So I have just a very brief recap here. Just to say conventional TIs are mostly bulk materials. And so this quasi 1D topological insulators, they basically have stacks of atomic chains. And so they have several advantages over conventional 3D TIs. For example, there's cleavage along multiple cleavage planes. The surface states are isotropic, and you can have the transition to strong TI, weak TI, and trivial insulators. And of course, they can also host high order topological states, as we heard from the talks on Monday. Okay, so in particular, so business iodide is one of belongs to this class of quasi 1D topological insulators. So they have periodic chains, atomic chains aligned on the B direction. So stack up the chains on the AB plane, and then there's then you stack up the planes along the C direction. So they have 2 cleavages, and so they actually also, as we heard from Monday, just to remind you, they have 2 different phases: alpha phase and beta phase. So there's the transition. This is data from Bing Lu's group. Well, actually, well, no, I think this is data taken from one of the papers. I think Bing Lu's group has similar data where there's a transition happening at around room temperature. So the alpha phase is actually the natural low temperature phase, and beta phase is the natural high temperature phase. So this beta phase has been predicted by Fan's group to be a weak TI, and this has been verified by the upper studies, including this beautiful work from Ming's group. This came out recently. Okay, so how about the alpha phase? So alpha phase, again, this is low temperature phase. So long thought to be trivial insulators. So recently, the Fan has the theoretical calculations that predicting has a high order topological hinge states, so they have a gapped and service states, bulk and service states. But so far, so there's upper studies again from Ming's group, which is consistent with this behavior. So far, the transport studies are open on bulk samples, and there are some perhaps somewhat strange data. For example, you see the Rx might change the sign multiple times as a function of temperature, etc. And there's also some order of magnitude difference in the resistivity value among the different measurements. Okay, so what we do, if you know me, I'm like a 2D materials person, so it's like occupational hazard. We see a layer material, we want to exfoliate it. Okay, so we had the bulk crystals, so exfoliate down to thin film. So we actually are not down to extremely thin films. It's not to monolayer or few layered image. But this is about 20 to 40 nanometer thick, and we encapsulate them with HBN, hexagonal boron nitride, just because this material is mildly air sensitive. So we cool them down in that we did not do any quenching, so they should remain in the alpha phase. Okay, so this is the transport data. So here we have the red curve here is plotting resistivity or resistance as a function of backgate voltage. And now we see there's actually this, first it's very gate tunable. So we see this resistive peak, it's almost like a Dirac-like peak. So it shows that you see the Dirac point, a very small gap. And the red axis, the blue curve, showing the Hall resistance, which can see that changes sign, which shows that it changes from electrons to hole-like B transport as a function of gate voltage. And here plotting the Hall resistance function of magnetic field. We see that it's actually, again, at different gate voltages. So you see the change of slope, showing again the carrier changes sign, and then it's actually fairly linear to find the so it's linear with magnetic field, which shows that it's basically it's like a Drew model. It's almost okay. It's like a Drew model, but strangely, what we just put in the numbers. The RXY is not given by this like the Drew model 1 over the charge density. Okay, so now if we just do the temperature dependent studies. So here we're plotting this RXX as a function of different temperature, as function of temperature at different magnetic fields. So top curve is close to the resistance peak, and the bottom curve is when it's highly electron doped. So when it's close to resistance peak, we see that it's really insulator-like, and when it's highly electron doped, it's really metallic. So resistance decreases, function decreasing temperature. There's a little small uptick at the end. Now, if you look at the Hall resistance, again, now this is again as a function of the temperature and different gate voltages. Now we also see that, okay, so the change of sign. Oops, okay, I did not show. But actually, if you look very closely at the one of the gate voltages very close to the crossover, actually, you can see at some gate voltage range, it will change sign multiple times as a function of temperature. Okay, so if we just look at this, so this tells us we have two different competing transport channels. One is a hole doped, basically insulator-like state, but we think it's a bulk state. Either the bulk state or some sort of surface state, but this basically should not be, this state should not a change as a function of gate voltage. The second channel is a gate-tunable metallic channel. And so this is a bipolar channel. We can use this, we can use the gate voltage to change the resistance of this channel. And so this, just to put this a little bit more quantitatively, we write the conductivity of the device as a function. It's a gate-tunable channel. Okay, so this is sigma G. So that this would be change a function of gate voltage and temperature. And the sum, and added to that is the parallel conductance channel. This is as a function, as a bulk channel, which only depend on temperature, but not gate voltage. Okay, so now you would take, so now we have all these different curves, and then you would just, we can just subtract them. Okay, so imagine subtract this, take two pair of curves and subtract them. And so that the bulk channel will subtract out. So what we're left with will just be the gate-tunable channel. And then we can normalize it to the difference in gate voltage and times the capacitance. So they should give us basically the mobility of the gate-tunable channel. Okay, so this is what we get. So we take this is several different pairs. We can see that they collapse onto the same curve, showing that yes, we do indeed have a gate-tunable channel. And this is one of the curves here might be hard to see. It's a solid curves basically fitting to a phonon limited scattering. So a low temperature is limited by impurities, so relatively temperature independent, and a high temperature is phonon limited with exponent. So the mobility goes to T to the power 1 minus 1.5. Okay, so we think so it's a phonon limited scattering when temperature is above 150 Kelvin or so. Okay, so these are our experimental observations. So we think we have a gate-tunable metallic transport channel. That channel is also ambipolar, so we can tune that by gate voltage, which means it has either a direct point or very small gap. Okay, so what is the origin of this gate-tunable state? Okay, we're saying, okay, so the trivial explanation will be maybe it's related to bulk band, the density in the surface layer. We tune the density in the surface layer by gate. Okay, so first this has to be not very doped. Then maybe we can tune part of this bulk band by gate. Or we can have maybe just actual surface state on the AB surface. Okay, so to try to see if that scenario is true, so what we do here is we try to only contact the bulk, meaning the inside of this surface. So what we do is we basically come in, so we encapsulate it with a HBM layer that has 3 pattern holes on the inside. So we put this HBM layer onto this iodide flake, and then we deposit metal. So in this case, we're really only contacting the inside, the bulk of this sample, and not to the edges. Okay, so then we can put a backgate, and we have backgate, which is silicon backgate, and now we can also put the top gate on. So with this sample, now we see actually has absolutely no dependence whatsoever on gate voltage. So we have backgate, we didn't even show. So backgate is in case, okay, we'll say maybe it's will be backgate voltage will be screened. But now, okay, we also have top gate voltage, we also have no dependence on top gate voltage, no dependence on magnetic field. Okay, so now we think, okay, therefore this gate-tunable channel is not related to these two trivial explanation. Okay, so now we're left with a more interesting explanation, which is, okay, so there's 3 possibilities. One is that we have the psi surface state on the BC surface. Okay, so this is, again, this is data from Ming's group. Sorry, no, this is not data Ming's. No, this is calculation from Fan's group, but I think Ming's group has data which confirms this, is that the AB surface is gapped, and then the B surface actually have a small gap. Okay, so this one has a larger gap, This one has a smaller gap. It's also anisotropic, have a Rashba-like spin splitting. So second possibility is a topological hinge state, which is drawn here. Okay, and then which is this higher order topological state. And third probability is that even though we are measuring this is 20 to 40 nanometer thick samples, I think from Fan's calculations, so it shows that the interlayer coupling is very weak. So we're effectively measuring the 2D, it's basically a topological insulator state in this decoupled monolayers. Okay, so but which one of this is true? So unfortunately, I cannot tell you that yet. So we are still working on that to try to distinguish between these different scenarios. But in any case, any of the scenarios are actually very interesting. So we'll be happy to just to find out which one it is. But what we again just to touch base to the title of my talk, so we can support supercurrent, and so we can use this gate-tunable channel for supercurrent in this device. So what we do is we basically just put a niobium contact to a specimen iodide flakes, and so here we're plotting is DVDI, so differential resistance, as a function of current bias. Okay, and also in this color graph here, the vertical axis is gate voltage. So we can see that we can, so it supports superconductivity. And so you can see this critical current is weakly gate-tunable. Well, so it's not a strong gate dependence, but nevertheless, there is a gate dependence, again, showing it's carried by this metallic channel. Okay, so we show we can support a gate-tunable supercurrent. And so I think it is possible to support topological superconductivity. Then this is well, after we make sure which of the three mechanisms, transport mechanisms is responsible. Okay, so all right, so okay, so next of my talk, I want to tell you probably very briefly of the helical edge states in field layer graphene. Okay, so here it's probably, let me show you this. One-layer graphene linear dispersion, bilayer graphene has a quadratic dispersion, and of three-layer graphene, this is ABA/trilayer graphene. This has a dispersion of 2+1 model, so meaning you have monolayer light band plus a bilayer light band. In tetralayer graphene, now you have 2+2 model, meaning you have 2 bilayer light band with different masses. Okay, so what's interesting is that basically this, just to remind you, these are semi-metals. And semi-metal is actually another way to get to achieve helical edge states. This is because, but we have to apply magnetic field to make the bulk insulating. So that's when the bulk insulating, actually a lot of the states, actually I will show, has already have the band inversion coming from the band structure, and so that it will give us helical edge states. So we can have helical edge states without spin-orbit coupling. So what's interesting about the graphene metallic system, semi-metal systems, is that they have the electronic state that is E equal to 0, and so this will give us a quantum Hall state at charge neutrality point that has no counterpart in the semiconductor 2-decks. So this state is extremely tunable, so you can apply a out-of-plane magnetic field to couple to the orbital degrees of freedom, in-plane magnetic field to couple to the spin degrees of freedom, an out-of-plane electric field that will break either the mirror reflection symmetry or the inversion symmetry that is couples to the layer of the valley degrees of freedom. And also we have the gates to keep them exactly at the charge neutrality point. Okay, so let me just tell you that we are looking at 3-layer and 4 layers. And so this work is, so there's 2 papers, but led by my student Shicha and Peter Svednov, and my fantastic theory collaborators, including Alan McDonald, Yafa Spalas, who was a postdoc at University of California, Riverside. Now he started a position in Nevada, and Herb Vertic at Indiana University, Alfred Sheshoni at Young University, and Gantaphy Murphy at University of Kentucky. Okay, so for AB stack trilayer graphene, basically has mirror reflection symmetry. So we can decompose this lattice into monolayer light band and the bilayer light band. Okay, so one of them has basically even parity with respect to the mirror reflection, and the other and the monolayer band out parity with respect to the mirror reflection. So we have multiple direct band. And so what happens is that when you include all the hopping parameters, the band structure is like this. You basically have the monolayer light band is now gapped, but it's shifted relative to bilayer light band, so that here you say you have so-called band inversion. So now here you have the electron holite state above the electron-like state. So now you apply okay. So this will give us a band inversion, but now we apply a magnetic field to make the bulk insulating, and so this will give us a helical edge states. Okay, so Landau was the N is here, so that we can keep the chemical potential between these two. This is charge neutrality point. We keep chemical potential between these two line levels. And so if you, as long as we do not apply any outer plane electric field, this band structure is protected by the mirror reflection symmetry. Okay, so this is our experimental data. We're plotting the longitudinal conductivity as a function of magnetic field, and this is outer plane electric field. So we can actually identify 4 different phases. So phases 1 through 3 are close to the 0 electric field. And phase 1 has quantized longitudinal conductivity of 4e²/h. Okay, so this is the zoom-in picture. And 2 have 2e²/h. Okay, and phase 3 and phase 4 are insulating. But then actually, if you go from phase 3 to phase 4, they are actually connected a region of a higher conductivity, which suggesting they have different symmetries. Okay, so this we work on this with Alan for actually I think almost 2-3 years on this, and we think we understand. You said again, what we have is basically from that band inversion happening. So this will give us a counter-propagating states, and they are protected. So what the degree of freedom they're carrying is this parity, which is protected by the again mirror reflection symmetry. And so each of this will give us 2 helical. So this will give us 2 helical edge states in phase 1. In phase 2, what happens is that when you apply the magnetic field, the self energy will cause one of the monolayer light band to move up, bilayer light band to move down. And so this is what we have. Therefore, we're going to, so they counter propagate like this. Therefore, only have 1 helical edge state. And phase 3 is that they continue to move. Eventually, we're just going to have a normal band. So this is 0 edge state. And phase 4 is where we break the mirror reflection symmetry. And so this gives us a layer porous insulator. We can also tune between phase 2 and 3 by an in-plane magnetic field. Okay, so the bringing this insulating state back to 2e²/h to this helical edge states. Okay, so this is okay. So this I'm probably going to run out of time. Let me just say that we note. So let me just say that this this state with 1 helical edge state, counter-propagating edge states. So it happens actually at relatively low field. So it happens between say 2 Tesla and 5 Tesla or 6 Tesla, depending if you apply my in-plane field or not. So that's actually a relatively friendly regime for experimentalists. We want to couple this to superconductors. Okay. So that's to realize them on a 0 mode. So maybe let me skip the tetralayer graphene. Let me just show you. We also similarly, we actually also see the tunable edge states. So these transitions and tunable edge states between 1, 0, 1, and 2 helical edge states. Again, tuned by electric field and magnetic field. Okay, so yeah, so we have this coordinate geometry to basically verify that. And let me just say that, okay, so well, so that I can get to the last 2 slides of my talk. Right, just to summarize this part of my talk, we have basically very much rich physics and Fourier graphene at charge neutrality point. So again, especially in trilayer graphene, there should be friendly experimental realization of Majorana zero mode, because we actually do not need 20 Tesla in plane field to achieve this helical edge state. So I only need a few Tesla, and that's compatible to a lot of superconductors critical field. All right, so lastly, let me tell you just this 2 slides. Our recent work, which we find really exciting, is the superconductivity in the flat band. This work led by my student, Haidong Tin, very close collaboration with Mark Barcroft. So we spent months thinking and discussing about this. And the theoretical work by my colleague Mohib and Dajria, again, Fanzhang's group at Dallas. All right, so this is again why the appetite to motivate what's driving this. It said, okay, so we all heard about flat band, especially in twisted bilayer graphene, when the band is very flat, the band velocity is slow, right? So the band velocity is very slow, but what does it mean when we have a flat band superconductor? So from the BCI theory of superconductivity, then actually when BF is 0, a lot of the things actually start to become funny, right? For example, superconducting gap is done by H bar VF divided by coherence length. And so VF 0, gap should be 0. If you use P-Parse argument for coherence length, right? So this again, they should give it 0. All right, maybe you say 0 divided by 0, maybe give a finite gap. All right, but how does this work? So superfluid stiffness, or called superfluid weight, again, conventional superconductors is given by this formula here. So this mass, so this mass is a mass of the Cooper pairs, and this NS is basically a superfluid density. But again, if you have a really, really flat band, the mass is going to approach infinity. Now you're going to have 0 superfluid stiffness, and therefore now all of this will just make the very appearance of superconductivity a paradox. Okay, so okay, so what we have seen, so this is the data from twisted bilayer graphene. So this is well, I'm showing this is 3/4 filling. This is about half filling. Okay, at the so there's my others I'm not showing, but in this area we're seeing this superconducting here. Okay, so this is plotting nonlinear transport, dVdi as a function of bias, and this is charge density measured from the half filling. What we see is that because I should say that we measure the filling velocity, which is very slow, which is about 1,000 meters per second. So which reduced from the monolayer graphene of 10 to the 6, right, by 3 orders of magnitude. And so now, what we find is several findings. First is that we find that there is this very small speed limit, right? And it's direct. So it's like we have a speed limit, like the speed of light, limiting how fast everything moves in the universe. So now this speed limit, this very slow speed limit in this twisted bilayer graphene is actually limiting the supercurrent density in the Stibach spectrum. And then now we have this actually very small, again, Fermi velocity, but again, we have seen a pretty reasonable superconductor, right? With the TC about 2.2 Kelvin at the top of the superconducting dome. And so we believe this is at least consistent with the superfluid stiffness arising from quantum geometry. So there's some theories on this. So I think this is recently being appreciated by the theorist. But interestingly, again, because we measure such a small Fermi velocity, the ratio of TC over TF is actually greater than 1 over, I would say, 95% of the entire dome is at the very edge. So this will put this superconductivity in a strongly coupled BEC like superfluid state. Okay, so with this, let me just thank my students and my group member and my collaborators and the funding agencies.
Time for a couple of short questions. I think Santo raised a hand first. Let me run them.
Thank you for the talk. So I'm very intrigued by your last slide.
Okay.
So most of the previous data on TBL, superconducting TBLG, TC over TF is big, but it's like some fraction of 1.
Mm-hmm.
Right? Pablo measures the effective mass. He knows the density, so he can extract out a Fermi energy. And TC is maybe 0.1, 0.2. So I'm wondering do you have a much higher TC?
We don't have a much higher TC, but we have much smaller TF. I think basically, I know Pablo's original paper measured a Fermi velocity is about 20,000 meters per second. And we measure actually much smaller than they would measure about 1,000. So I think, yeah. So I think so you asked me why Pablo's going to not see it.
No, can I just
sure,
say something?
yes.
So there's a measurement of the Fermi velocity, which is the Dirac velocity near neutrality.
Mm-hmm.
But then Pablo also has a measurement of the effective mass directly from the temperature dependence of the Landau fan.
Yes.
Right, and that's what he uses to extract out the Fermi energy. That's the density of charge carriers from both Hall and Chumnikov-Dehas, and the effective mass from the same measurement.
Yes, yes.
Right, and that's a different mass from the one that enters Fermi velocity. The Dirac node velocity.
The what?
The Dirac velocity near neutrality.
Mm-hmm.
Right? So, do you have a measurement of the mass in the superconducting?
Yeah, so close to, right, where we can measure as a function of density, which when that looks like it's actually pretty massive, massive particle. Right, so close to this superconductor, basically in this same density regime.
So maybe I can pass this slide here. So what is the scale? So my understanding of the usual Fermi energies like 10 MeV.
Mm-hmm. This is like on the order of milli-electron volt or smaller. Yeah. Again, it's somewhat density dependent. But I would say around this area.
Okay.
Yeah.
Thank you.
Hi, I have a question about the earlier part. So with the helical edges in the trilayer system. So I mean, one of the things that has been an issue with the helical edges in other 2D systems is that they don't seem to be ballistic as you would expect of large scale. So can you test that? And the second question is, can you actually sort of nano engineer these things? Because one of the things that I thought would be a really fun thing to do is if I take a bunch of 2D TIs and I put them very close to each other, then you could run a current in one and induce circulation in the next one, and you could sort of make gears with Coulomb drag. And so, we proposed this, but with the Mercury system, it's a big pain.
Yeah, so I think, okay, so I should say that this graphene by itself without magnetic field, of course, the helical, there's no really edge state. But in the quantum Hall state, because this graphene system is so clean, we see oscillations at 0.1 Tesla or something, right? Or smaller than that. Tens of millitesla, and so the Trilayer system, I think in the quantum Hall, it just really in few Tesla is like great quantum Hall system. It is ballistic and all that. I think that's why we are able to see this helical edge state. We measure this. You actually measure instead of chiral, which you measure zero resistance, we measure quantized resistance.
But the samples are exfoliated, so they're micron-sized plates, or
they are on the order of I think 5 times 20 microns.
Okay.
Yeah, They are decent size.
So I mean, could you do this thing with putting different pieces?
Well, yes, I think in principle you can. You will probably need to pattern different gates and all that. I think yes, that should be doable. Again, that's one beautiful thing about I always say graphene. It's very tunable. Yeah, yeah.
Okay. Last question.
Yes, I have a question regarding your high order TI part. You have
Okay.
a picture that you're showing these helical modes.
Mhm.
Have you tried to apply in plane magnetic field?
Ah, that's good.
Because if you do that, then you can get corners. You can
That's a
gap
good
the
question.
edge.
No,
Yeah.
we have, no, we have not. That's a great suggestion. Thank you.
Thank you, Jeanie. So while Santo is setting up, and maybe I can make an announcement. So in the afternoon, the session would finish around 3. At 4 o'clock in the department, takes a little bit of traveling. There's a special lecture that's going to be given by Professor Sang-Woo Chung. And I think the title is the Emerging Phenomena and Broken Symmetries, if I'm remembering correctly. Everybody's welcome to join it. And there will be a reception after the lecture. And so if you want to go there, just find a local person probably is driving. We'll get you there.